Very good morning, students. In the last class, we have discussed about collision, right? Whenever two bodies collide each other, they will exert equal and opposite force according to Newton's third law, and this gives there is a change in the shape of the object. This collision make a changes in the shape of the objects, right? That change in the shape gives rise to new force, that is elastic force, right? And that elastic force is responsible for the rebound of the object. That is, in collision, the object, whenever they will collide, they will rebound with some other velocities. Okay, this elastic force is responsible for the rebound of the objects or the bodies, right? Fine. In collision, we have discussed mainly two types of the collision, that is elastic collision and inelastic collision. What is elastic collision? In elastic collision, that is both linear momentum and the kinetic energy of the particle is conserved in case of elastic collision. And in case of inelastic collision, only linear momentum of the system is conserved, and but the kinetic energy of the system is not conserved. Right? And in elastic collision, example for the elastic collision is atomic and subatomic particles. We can see elastic collision in only atomic and subatomic particle. In that case only, the total kinetic energy is transferred in case of atoms, molecules and subatomic particles like proton and neutron. But in inelastic collision, the like example of the plastic collision of the two plastic bodies, collision of mud and ball, right? In that case, the kinetic energy of the particle is not conserved. Only the linear momentum of the system is conserved. So total linear momentum of the system is conserved, whereas the kinetic energy of the system is not conserved. This we have discussed in the last class, and also we have derived an important derivation for the collision, elastic collision, right? So in today's class, let us learn about inelastic collision. As I already said, we will derive expression for the inelastic collision with the particles, right? So inelastic collision here, only linear momentum of the system is conserved, but the kinetic energy is not conserved, right? We will consider again two bodies of mass m1 and m2. Let this have initial velocity u1 and this body has initial velocity u2, and they are moving on a straight line. That is one dimensional motion or head-on collision. One dimensional motion or head-on collision. If the particle initial velocity and the after velocity are on the same straight line, if they are on the same straight line, then such type of velocity, such type of collision, we can call it as 1D collision or head-on collision. 1D means one dimensional collision and or head-on collision. Fine. So after collision, in case of inelastic collision, what happens? After collision, it will change its velocity because of the change in the configuration, and we will get that velocity v1 and v2 are the velocities after the collision. If the collision is perfectly inelastic, if the collision is perfectly inelastic, now we are discussing inelastic collision. If this collision it is before collision and it is after collision. If the collision is perfectly inelastic collision, then these two bodies will stick together. They will move together with a common velocity v. Now they have velocity v1 and v2. If the collision is completely inelastic, the two bodies will move together with a common velocities v. With a common velocity v. Now let us say, consider two bodies of mass m1 and m2 having initial velocity u1 and u2, right? Then let v1 and v2 be the velocities of the bodies after collision. Now, the total linear momentum of the system is given. It is the total linear momentum of the system is given by m1 v1 plus m2 v2 is equals to, say in case of inelastic collision, as I already said, the total linear momentum of the system is remains conserved. It is conserved. Therefore, m1 plus m1 v1 plus m2 v2 is equals to m1 u1, and let the mass m2 be at rest initially. Therefore, initial velocity of u2 becomes 0. If m2 is at rest initially, then that u2 becomes 0. Therefore, before collision is equals to after collision. Therefore, here conservation of linear momentum. Conservation of linear momentum. But here kinetic energy is not conserved. Now let us write for that one. That is half m1 v1 square plus half m2 v2 square. This is the kinetic energy after collision. This is the kinetic energy of the particle after collision, and this is not equal, but it is less than initial kinetic energy of m1 u1 square. That is, initially it has greater kinetic energy. After collision, the kinetic energy becomes less. After collision, the kinetic energy is less than before collision. The kinetic energy before collision. Right? Now let us calculate for equation number 1. That is m1 v1 plus m2 v2 equals to m1 u1. Right? For that, now let us calculate that one. If collision is, as I already said, if the collision is completely inelastic, if the collision is completely inelastic, or you can say perfectly inelastic, then m1 the mass m1 and m2 move together. The two bodies move together with a common velocity v, with a common velocity v, that is v1 equals to v2 equals to v in case of perfectly inelastic collision. Therefore, here I will substitute v1 equals to v and v2 equals to v. Right? Substituting v1 and v2 as v in case of equation number. Consider this as equation number. You can consider this as equation number 1 and it as 2. Right? In equation number 1, we substitute v1 and v2 as v. Fine. m1 v plus m2 v is equals to m1 u1. Now here also I have v, here also I have. I will take v common. What I will get? V equals to m1 plus m2. That is equals to m1 u1. I can write v equals to m1 u1 divided by m1 plus m2. This gives the velocities of the particle of the collision. That is common velocity we will get. That is, if the collision is completely inelastic collision, perfectly inelastic collision, then both the objects will have common velocity. That is, they will stick together, they will move together. Therefore, we have for both bodies we will have only one velocity. That is given by v equals to m1 u1 divided by m1 plus m2. Now, In case of inelastic collision, that is kinetic energy is not equal, that is kinetic energy is not conserved, that is the total kinetic energy is not transferred. Before collision, the what the object has the kinetic energy, that total kinetic energy is not transferred to the after collision. That means that there is some loss of kinetic energy. Let us calculate now that change in the kinetic energy. Let us calculate that change in the kinetic energy. Delta K I will take. Let us calculate the change in the kinetic energy or the loss of the kinetic energy. Loss of kinetic energy in case of inelastic collision. Loss of kinetic energy in case of inelastic collision. That is delta K equals to half m1 u1 square minus half m2 v2 square, half m2 v2 square. So here I will write it as, we will get both the bodies, that is m1 plus m2 v square, m1 plus m2 v square, that is these two bodies with the common velocity. Now we already know the value of v here. Now let us substitute this value of v in this equation. That is, we will get delta k equals to half m1 u1 square minus half m1 plus m2 into v square is there. V means what we have here? m1 u1 divided by m1 plus m2. m1 u1 divided by m1 plus m2 whole square. I have substituted the value of v in this equation. The value of v is m1 u1 divided by m1 plus m2 square is the whole square. Now, I can write this equation as half m1 u1 square minus half m1 plus m2 m1 u1 square u1 square divided by m1 plus m2 whole square, m1 plus m2 whole square. And m1 plus m2 and m1 plus m2 cancel each other. The remaining thing is here half m1 u1 square minus of half m1 square u1 square divided by m1 plus m2 we will get. Now take common 1 by 2 m1 u1 square, here also 1 by 2 m1 u1 square. Taking common here, that is change in the kinetic energy or loss of kinetic energy is given by half m1 u1 square. That is here m1 u1 square common. Then remaining thing is here 1 minus of, here m1 u1 square is there. Already 1 m1 I took outside. So remaining is here only m1 divided by m1 plus m2 divided by m1 plus m2. Fine. Now delta k is equals to 1 by 2 m1 u1 as it is. Here we take the LCM. Okay, after taking LCM we will get m1 plus m2. Numerator we will get m1 plus m2 minus of m1. Then m1 get cancelled plus m1 minus m1 get cancelled. Then remaining thing is delta k equals to delta K equals to half M1 U1 square into M2 divided by M1 plus M2. M2 divided by M1 plus M2. This I can write it as half M1 M2 divided by M1 plus M2 into, because this equation we can write like this. That is loss of kinetic energy in case of inelastic collision. The loss of kinetic energy in case of inelastic collision is given by this delta K equals to half M1 M2 divided by M1 plus M2 into U1 square. Clear? Oh, now this is in case of one-dimensional collision. This is in case of one dimension. Now let us calculate elastic collision in case of two dimension. Elastic collision in case of two dimension. Collision in two dimension. Write the heading, collision in two dimension. Collision in two dimensions. What happens in two dimensions? We have mass M1. It will collide with particle M2. Okay. It is having initial velocity u1. Let us assume this particle is at rest. Therefore, u2 equals to 0. Okay. Now, collision in two dimension I want. Collision in two dimension means after collision, this particle will move in two axes. One is in x-axis, another one is in y-axis. After collision, what happens? These particles will move in two different axes, x and y-axis. Okay. This is, I will take as y-axis, and this I will take it as x-axis. After collision, this particle will move in perpendicular direction with the velocity m1. With the velocity m1, let the body m1 have the velocity v1 and body 2 m2 has the velocity v2. Right, by making an angle here, theta 1 and theta 2. They will move in the two dimension. They will move in two dimensions. This along x-axis also. The position of this particle is along x-axis and also in y-axis. And second particle is also posing x-axis and negative y-axis. Clear? Now, the component of this first particle, the component of the first particle along x-axis and y-axis is given as the component of the particle 1 along x-axis and y-axis is given as m1 linear momentum, m1 u1, the linear momentum of the particle 1. Or you can say it is momentum, not linear, it is momentum. The momentum of particle 1 is given by m1 v1 cos theta, m1 v1 cos theta 1, that is along x-axis, and also m1 v1 sin theta 1, it is along y-axis, right. Similarly, the momentum of the particle, the momentum of the particle 2 is given by m2 v2 cos theta 2. The momentum of the particle 2, m2 v2 into cos theta 2 along x-axis, and minus of m2 v2 sin theta 2. Why I am taking a minus sign? Because this particle is in the negative y-axis. Therefore, m2 v2 sin theta 2, it is along y-axis. Clear this much? So now, the linear momentum of the particle is given by, that is according to the principle of conservation of linear momentum. According to the conservation of linear momentum before collision is equals to linear momentum after collision. Now, write that by principle of conservation of linear momentum. By the principle of conservation of linear momentum, we will get this. Before collision, we have m1 u1 is the momentum of the particle, then that is equals to, before collision the momentum of the particle is m1 u1, that is equals to linear momentum after collision or linear, because it is not going in a straight line, right? The momentum of the particle in two dimensions, it is given by m1 v1 cos theta, m1 v1 cos theta 1 plus m2 v2 cos theta 2. It is along x-axis. Now, along y-axis. Now let us consider the total momentum of the particle along y-axis. Along y-axis, this particle is not moving in the y-axis; it is only in the x-axis. Therefore, here along y-axis, I will take m1 u1 as 0. Right? m1 u1 as 0. Now, along y-axis, I have the particle for particle 1. I have here m1 v1 sin theta 1. m1 v1 sin theta 1, and particle 2, this is I have here, that is m2 v2 sin theta 2 minus of m2 v2 sin theta 2. This along y-axis. This I will get along y-axis. Clear? Now, if the collision is elastic, then if collision is collision is elastic. Then kinetic energy of this particle is given by half m1 u1 square is equals to half m1 v1 square minus half m2 v2 square. For elastic collision, we will get kinetic energy is conserved. That is half m1 u1 square is equals to half m1 v1 square minus of half m2 v2 square. Clear? So this was the last concept of work energy power. So here we have completed your work energy power lesson, right? So we will discuss next lesson in next class. Until then,